Where should we start? Let's try. I'm getting lost in my. That's my thing. Okay, so we're still looking at algorithms, and one that we want to look at is in more detail, which is something that you should have seen in your first year, but that's long ago. That was the shortest path in that. Okay. But okay, so before we get there, this is like a warm-up. Okay. So the least element is you get basically an array of things indexed by some index set. And you're trying to find for which of these indices the value is the smallest. Okay, the array is a rational numbers. So I'll formalize it mathematically as a function going from the index set to rational numbers, which means for each of the indices, there's exactly one value. You want to find for which index is the value is the least one. Okay, so the input is a non-empty finite set. Of indices. Okay. And a function mapping f, which to every index gives you a rational number. Now you can't really do real numbers in the computer because there are too many. So we think all numbers in the computer should be rational. And the question is for which s in the index set is the value for that index in that array, is equal to the least possible value among all things in the set. Okay. So this is written in the maths notation, but the meaning is really you've got a finite list of numbers, and you want to know which one of them is the smallest. Okay, so if I write 2, 17. Which is the smallest number? Oh. Have you found the smallest number there?
I don't know. Very challenging.
Yes,
I think so.
Yeah. How did you find it?
I looked in the array.
So it was kind of like 2.
Sort of, yeah.
That's what normally people do. Humans, they do like 2. Well, the computer can't do it like that.
The computer hit the board.
So I'll try to demonstrate.
Do the minimum that says to carry it over to the next bit. Carry it over.
Like you said, it must do some sort of reorder.
You're too advanced.
Ready.
So stop. What is it doing? It's not showing yet.
Ready.
Okay, so now give me the least number that you will see among the numbers that will show. Okay.
It's going to be a very big matrix of numbers now. Ready.
Okay, so it's largest, but when I said smallest, so you should concentrate.
3 and 4.
3. Yes.
Oh, biggest was 48.
So how would you do it?
Like I was explaining before you started that.
Yeah, but you were too ahead. You wanted to spoil my little demonstration. Okay, so this is how it works. You, the computer just looks at each of the entries and keeps track of whichever was the smallest one that it encountered, and then in the end, it spits out the answer. So if you wanted to write the algorithm, it would be something like this. So first, it says that m is plus infinity, so that's the first thing, and s is nothing, none, say. And then it does a loop where it goes through all t in set s, and it does if what I'm looking at the moment is smaller than the minimum so far, then that's the new minimum. So I say S is T, M F T, the new minimum. Then that ends the loop, and then it gives back. Yes. Formally written, total formally. The algorithm for this book. Do you agree?
Mm-hmm.
Yeah? Right, so we talked about analyzing algorithms. And there are two main things that one has to look at when analyzing an algorithm. Do you remember what they were? The first one is it correct?
And then
Which
how efficient.
also has, yeah, and the second one is how efficient is it?
I found it.
So correctness has two parts. A is, does it stop? So this one stops because you've got, so how could it not stop?
Infinite list of integers.
You get a finite set S, and you just look at each of them once in the loop. So the loop can't run forever, return can't run forever, and do assignments can't run forever. So yes, it clearly stops. And does it return the correct answer? Well, yes, because at any point in the run of the algorithm, M is the least value that it's ever seen, and S is the index of the least value that it's ever seen. C is something that's smaller than it's seen so far, you replaces it, and so in the end, it will have the smallest value. So, yes, of course. How efficient is it? So, how many steps does it take?
A set.
Okay, so if, yeah, so exactly, depending on the input side, that's the right idea. So we can say that there are n elements, n indices, and let's think that the rational numbers are all kind of limited in size. So all these are elementary operations, as we said, the assignments, the comparison, assignment. Okay, so and return a number, an elementary operation. So it does two elementary operations to initialize. Then this loop runs n times. Okay. And in that loop, well, it initializes, so it puts something into t, so that's one operation. Okay. Then perhaps we can see it looks up f of t, so that's another operation. Then it compares it to m, so that's another operation. Then maybe, or maybe not, it does these two operations. Okay, and that's it. So it does 3 or 5, depending on whether things, so it's something between. And then it does 1 here. Okay, so the number of elementary is certainly not more than 5n plus 3 or something like that. Okay? We don't really want to get into all these details, whether it's 2 or 3 or whatever. So what we're going to say is that this is definitely big O of n using the orientation. Okay, so it's bounded by some constant times n. So finish the sentence. The algorithm runs in. Okay, so that's an example how you do the O thing, because you don't want to get into too much detail about whether it's 3n, 5n, 7n, doesn't really matter. It's reasonably efficient because O of n is kind of the least thing, because you have to look at each of the numbers, and that's already O of n. Okay, that's already n elementary operations, so you can't possibly get away with fewer than n operations. And so O of n is the best possible. Okay. Any questions about this? Shall we move on to shortest path? Yeah. No one's watching. Kind of a bleak day. Okay. Does that need any more explanation, or is that it? Yeah, so probably remember that you had, I'm making this one up so it'll be a disaster. So you were looking at networks in the first year, and one of the problems, there were several problems. One of them was shortest path. Right, from U to B, and visualizing them as being parallel parts in the graph, but they could be because, and then there was an A. I'll just randomly put. A, mine. Okay. Probably remember how it went. But if not, I know everybody's copying that. Just randomly. So the way this worked was U, A, B, C. And then there was some distance, which changes. Roughly the way it works is it says, well, U is in distance 0. Yeah. And now, and we're already sure that U is in distance 0, so it kind of says, well, we're sure. And the neighbors, it says, well, A is in distance 3, I think, and B is distance 4, I think, and all these I don't know, so I'm thinking they're in distance infinity. For lack of better knowledge. Okay, this is how the algorithm starts. Okay. Now, what it does is now it uses the least element. Because among all those where it's not yet sure, it takes the least value. That's the 3 again. Okay. And it says, okay, so with A, now I'm sure. And it looks at all neighbors of A. U is already sure. C, I could get to A in 3, and then I can continue to C in 5. So C is not worse than 8. And E is not worse than 13. Okay, and that's A's job done. And then it continues in the same way. That's one big loop. Yeah. Okay, so next, so this is the loop which in the algorithm as it's written is between 5 and 11. So on line 6 it finds the least number here, which which in this case is the 4. So it says B is, I'm sure, it puts it into P, it's called permanent. So the distance is now permanent to B. We know it's 4. It has to look at neighbors of B, and it updates. So it can't update because that's already sure. C is distance 11, but we already know that C, we can get to C in length 8. So I don't want to update it to 11. That's worse. And D, I can update to 12. Infinity, that's progress. Okay. And on it goes. So C is distance 8. Now, E can be updated to 10 from 13 because C is 8 and plus 2 is better, and F should be updated to 12.
He doesn't go much further. We change the
Yeah, no.
models.
So the next one is E, I think. B is 12.
11.
F is 11.
That's it. Go through the rest of the circle. Engine form.
The next one is F. Doesn't change anything. And once I've circled B, I can stop because I know I can't do any better. Okay? And that's described here. So you just think of the meanings. P, set P is the vertices that I've already circled when I was demonstrating it, and T is that I haven't circled yet. T are temporary ones. T for temporary. It means that the distance they have assigned can still change, so it's temporary. Whereas the P is the set of permanent vertices. So they can't change anymore. And the way it works is I always find the smallest temporary vertex, which is closest to you, make it permanent, and look at its neighbors, whether I can get there faster from where I am. Okay. And Philip proved that it works, I think. I'm not sure whether he did this, but okay, so we can have a look at, so this is O of 1, because it's just one operation. Here we're looking up things for each vertex. So I'll say O of n, n is the number of vertices. The n, the number of vertices. This again is O of 1. Now there's a loop. I have to. How many times do I do this loop? Stop it on.
Definitely end. But
Yeah.
isn't it still to do with how many nodes we've got? It's about the input size.
Exactly. So like here, this thing is done about n times for every vertex you put it. It's one letter, it's of n, roughly n, order of n. So this, there is a key thing is that every time you do this loop, you make this set smaller by one. Okay. So you start with a set which is roughly n vertices, where it's n minus one, and you keep doing it. Maybe not all the way until it's empty, but definitely not longer than n minus one times. So I don't care that it's n minus one times at most. What I say is this runs O(n) times. Okay? In keeping with nice asymptotic
distance from set D.
Which one?
So dV.
Oh no, that's the number in the table.
Yeah.
Okay, so this is D of something. That's why I keep it in the little table. And the distances on the edges is W. Okay? That's what contains them. Okay, so yeah, so sorry. Okay, so the things within the loop, this is obviously O of 1. That's just two operations. This little loop is O of n times, because it looks all the vertices, it could be less than n. Okay. And each of these is, okay, so I have to add something, compare something, maybe assign something, add something. So that's a constant number of operations, doesn't depend on how many vertices I have. Yeah, so 4 or 5, something like that. But definitely O of 1. So this whole loop is O of n times O of 1, which is O of n. Multiply them like that. This, what's the runtime of this? The test. So how fast can I find the smallest number in an array?
Oh, I love
this.
this.
Well, then, yeah. So this is O of n. This is O of 1 as well. Something. Doesn't depend on I'm just looking at one, well, kind of. But I'm just looking at one place in the memory, so that doesn't depend on how many things I have in the table. Just give me it. So what do we have? So it's kind of n times. This would be O n squared plus O of n plus 3 times O of 1.
Oh, you can just write up here. It's fine.
Okay.
I don't know where you got all the square from.
It's the bit in the middle.
Because-
the while loop.
Because I do O n times this loop. And each iteration of the loop takes O n plus O 1 plus O n, which is O n.
Yeah.
So O n times O n. It really works like that. It's explained in the book, so I don't want to spend much more time on this. But if you have two functions and each of them is linear, when you multiply them, what you get is that thing. So with this, we don't write it like that because n squared dominates. Okay. This is much less than n squared. It's less than n squared, so that's the running time.
That's the greatest running time. Is that how you would sort of interpret it?
Pardon?
Is that how you would interpret it? Like, that's the greatest running time? Because obviously 301 ON are less than ON squared.
Yeah.
Yeah.
So they somehow get consumed.
N plus 1 squared.
Yeah.
Plus 3.
That's not all right. So what you're really getting is only a very small window into this bit of a view of what complexity theorists do in algorithms. Kind of hard the first time to see it. So yeah. But this is how it works. And that's worse. Okay, so in particular, we were I said last week that we're interested in the distinction. About the distinction between polynomial time and worse than polynomial time. Okay, this polynomial time.
No.
Not.
Right. Oh. So polynomial. Oh wait, maybe.
Yes.
Yeah. This is not that. Need another sheet saying no.
No. Okay, so this is good because we said that polynomial time is, for practical purposes, is usually good, and you can really do it in real life quite efficiently. And in fact, okay, you have to get a bit more sophisticated if you want to do really big graphs like Google Maps, find me the shortest driving route. Okay. But this is at the heart of things. Except they because they optimize them, they treat different vertices differently because some of them are major junctions, some of them are just small, so they don't like that. But the essence goes down to the ideas. So this is why SOCNAP works. Okay, just a brief note on some of these. Now, you should explain to me what dynamic programming is. But, dynamic programming is like shortest knots. So what was the dynamic problem that you looked at with Philip first? Was it knapsack?
Yes. Yeah.
Okay. So perhaps we can say we want to maximize. Just stick to this one. It doesn't really matter what it is. 5x1 plus 4x2. 4x2. was 6x3, and the constraint there is that if you look 3x1 plus 3x2 plus 4x3, something more than 8, and I is 0 or 1. I 1, 2, 3. Okay, so a prototypical knapsack problem. So what I'm doing now is drawing the graph. It's a directed graph, but directed or undirected, it doesn't really matter. In directed graph, you have to follow the arrows, not go against when looking for the shortest path. So where the algorithm changes is it doesn't really change very much. Just want to show it very briefly. So in the situation that we had, where there were no arrows on the edges, this function was sort of symmetric, so it didn't matter when you put kj or jk. But in a directed graph, you have to be careful. So kj is infinity if there's no arc that way. So kj only goes from k to j. That's the distance from k to j. And if it's an arc, directed arc, then it's something else than w of jk. But that's the only spot where you have to be careful. Otherwise, the algorithm works exactly the same as for the undirected version. Okay. Putting a bit too much into this. Okay. Okay. So how does it work? So you're starting in a vertex or node, which is called 0, 8. Right. And it's kind of stage 0, state 8 in dynamic programming terminology. And from here, you can either decide that you're taking the first item, okay, and that would be walking along this edge to stage 1, and state is 5. Because if you've taken it, then you're using 3 capacity out of 8, so you're left with 5 capacity. Kind of. Stay there.